Hello. What do we do for number one of this warm up? How do we solve this? Or what does this mean? What does it mean if exponents are it's a prime factorization? If it's a perfect square, what do we know? We talked about this. This was right at the end of yesterday when we talked about the locker problem. What do we got? Strong showing right out the gate. Yeah, Ashmita.
They have to be an odd number of factors.
Yeah, if it's a perfect square, we know that it's an odd number of factors. Odd number of factors. Okay, for this next one, what did you guys get for the prime factorization of 5,400? What a large number. What we get?
I got 30 root 6.
No, not the square. We're not doing the square root of 5,400. We're doing the prime factorization.
I got 3 to the power of 3 times 2 to the power of 3 times 5 squared.
2 to the power of 3 and 5 squared.
Yeah.
Okay. Yeah, I mean, that would make sense with Adon's answer of getting 30 squared roots of 6, right? We can get a 30 out of that and then left over 6. Cool. What is the total number of divisors of 5,400 that are not multiples of any perfect square greater than 1? So 1's allowed, right? This is another example where I'd really like complementary counting. How many total divisors are there? So total divisors. What do we get for that?
48.
48. Yeah, I agree. You add 1, so this is 4 for the 2's, 4 for the 3's, 3's for the 5's. So I get 48. Okay, how many would have a multiple of a perfect square? How can we figure that out? Or maybe it is easier to go the other way. Let's see what the answer is real quick. Or not, because it won't let me click. 8. Maybe it is easier to go the other way. I don't know if I want to try to count 40 different examples. Okay, so if we know that we can't have a perfect square, let's think about it like this. We don't want a perfect square to be a divisor. What is the highest power of a number we could have then? Oh, okay, you're throwing it in chat. I thought we were still talking. No, we want it to not have a perfect square as a divisor. What would that look like? 30. 30 is the greatest factor? Sure. 30 is 2 to the first times 3 to the first times 5 to the first. Why is 30 the highest divisor that I could have? 30 or under is the highest. Why is that the highest possibility?
Because if you have anything, like if your exponents are higher than 1, then you have at least even exponent in
Yeah,
one of the divisors.
I 100% agree. If we have anything bigger than 1 here, then this becomes essentially you'd get a perfect square is one of the divisors. So this is 2 times 2 times 2, which gives us 8. So just kidding, complementary counting, not a good way to go here. We want to just go with the smaller version of this. Okay? Still confused, fair enough. So what this said is we want it to be a divisor that is not a multiple of a perfect square, right? If we were to have a multiple of a perfect square, then this would not work. So a perfect square means that it would have 2 to the second, or 3 to the second, or 5 to the second, or a combination of multiple of those, right? And that's why as soon as I said, oh, we have 48 divisors, maybe let's take away the complement. It's like, well, we'd have to figure out how many would have 2, how many would have 3, how many would have 5, and then combinations of that. It became more work finding the complement. So as Ananya said, the highest power we could have and have it not be a perfect square would be to the first power. this number is not divisible by any perfect square. And anything smaller than this number, which is 30, would also not have any divisors that were a perfect square other than 1, right? We're allowed to have 1. And so this just becomes 2 divisors from the 2, 2 divisors from the 3, and then 2 divisors from the 5. So that gets us a total of 8 divisors. And so we just got 8 as the total number of divisors, where they would not be multiples of perfect squares. Questions, comments, concerns there? Okay. All right. So let me pause this for some housekeeping. What does it mean for 2 numbers to have a GCD of 1?
They're prime numbers.
Yeah, they're relatively
They're
prime.
relatively prime.
I agree. That means 2 numbers are relatively prime. Now, we talked about two numbers are relatively prime. We talked about this yesterday in terms of looking at when numbers weren't relatively prime, and we could essentially figure out a GCD by using the Euclidean algorithm to kind of simplify down. Well, this works even if they are prime, even if they're prime together. The only difference there is that these numbers then must be essentially simplified down to some difference of 1. Let's look at what this could look like in an equation. So we have 19x plus 17y equals 1. This is what we're going to do. There is one solution to this, at least, maybe more. But I would say there's at least one solution to this, in which we're talking about an integer coordinate, right? We know there's technically an infinite amount of solutions to this, but we care specifically about an integer coordinate that will make this work. We know if we graph this, we'll have plenty of integer coordinates, but we're looking for 1. So let's try to figure 1 out. Now, let's think about how we could break down 19. What is 19 equal to? Anyone got what is 19 equal to? In terms of 17.
17 plus
17 plus 2.
17 plus 2. Good. Yeah, that's probably a bigger question. So then what's 17 equal to? In terms of 2 and other things. 2 times
17 over 2.
Yeah, we want to kind of see if we have any remainders. Okay. So how many times can it go imperfectly, and then what's the remainder from there?
8 plus
Remainder
1.
1.
8 plus a remainder of 1. Are we okay with that? Yeah? Does that make sense to us? We're essentially just breaking down 19 into 17 and 2. And I said, okay, well, now we'll go from 17. 17 is 2 groups of 8 plus 1. So let's talk about 2. 2 is equal to 19 minus 17. Are we all in agreement with that? Cool. So if that's true, why don't we sub this out for 19 minus 17? And then how did I get 2? 2 was whatever was left over. I said 17 can go into 19 once, and then it has a remainder of 2. And then I said, well, 2 can go into 17 8 times, and then it has a remainder of 1. But remember, I want this to equal 1. So let's multiply this out. This is 19 times 8 minus 17 times 8 plus 1 equals 17. Now, again, I'm trying to solve for 1. We want to eventually end up with 1 equals. So we're going to add the 17 times 8 to both sides. So that gives me 17 times 9 equals 19 times 8 plus 1. And then I subtract 19 times 8. So it's 17 times 9 minus 19 times 8. Now we notice here maybe that this is not necessarily not the same exact way we had this. Let's manipulate this to get it to look like our equation over there. What would we have to do to the x or the 8 and everything like that? How could we manipulate this equation to look like the one in this top left?
You can say 8 is x and y is 9.
Close, very close. Olivia?
X is -8.
Yeah, if we rewrite this as 19 times -8 plus 17 times 9 is equal to 1. Now we realize x could be -8 and y could be 9. So we could get the coordinate -8, comma 9. What do we think about that?
I have a question.
Sure.
How did you get rid of the +1?
How did I get rid of the +1? Oh, over here? I didn't get rid of it. I just had it equal 1. So essentially, like, kind of think of like 1 just as another variable you're solving for, right? Like I had 1, I still had 1, I still had 1. And now I said, well, let's isolate for 1 because I want it to equal 1. So then I subtracted, or I added over the 17 times 8, and then I subtracted over the 19 times 8, and then I had 1 isolated by itself. And so I get this coordinate. And this is a solution. Olivia.
Would it work if you scale?
Yeah, let's look at that. What if we made this -16 and 18, right? Does that still work? 19 times -16 plus 17 times -18. Oh, sorry, +18. Oh, now we get 2. So if we're scaling the numbers, we're going to end up with scaling the solution, right? We'd have to multiply everything by that scale. What do we think? We obviously want another one, right? This is we're not satisfied with this. This is not slaked our thirst. Yeah, cool, but you never thought of it on your own. Trust me, that's the exact same thing when I saw this. I was like, there is no way that you would have gotten me to do this. Yeah.
You understand, like when you did 17 equals 9 times 8 minus 7 times 8 plus 1, then why did you like add 7 times 8 and subtract 19.8? And then what was
17 times 8. Okay, so my original goal is to simplify down to 1, right? We noticed how in our original equation, this equaled 1, so we wanted this to equal 1, right?
Okay.
So now I said, my goal is I need to get my final solution in terms of 19s and 17s. And so I have a 17 and a 19, and then I have a 2. I don't really want a 2. 2 isn't really helpful for us, right? We want to get into groups of 19 and 17. But I need to do that to whittle it down and essentially end up with 19 and 17s. So we get a 2. We say 2 times 8 equals 17, and then we got our 1. That's what we really want. We want the end difference of 1. And so we then had to say, okay, well, instead of a 2, I'll make that 19 minus 17. And now I just have 19s and 17s or multiples thereof. And I was able to solve. This is definitely something that it took me a couple tries. Is this considered number theory? Yeah. Could you do this for something not equal to 1? Yes, but the big reason we wanted 1 is because we know by equaling 1, they're relatively prime, right? And so that was the big thing. We know we can do this because they're relatively prime. If they're not relatively prime, we'd really just be like finding a difference of them, right? Does that make sense? You'd still try to be shooting for that number, but it would be harder to get to it because you're saying like these are off by so many. I think the same idea would apply, but it's not necessarily as easy to deal with. Okay, let's deal with another one. What if I had 210x plus 143y equals 1? Okay, so I think we can tell 210 and 143 are relatively prime. We know that this is made up a whole bunch of primes, but this is essentially 11 times 13, and this is 2 times 3 times 5 times 7. Are we okay with that? Recognizing that these two numbers have to be relatively prime. Okay. So now we're going to do Euclidean algorithm. 210 minus 143 is equal to what? How does that break down to us? Someone give me numbers.
67.
67? Okay, I think 67 is all we can do with that, right? Obviously, if we were to subtract more than more groups of 143, it would not work. So now we go 143 because that's our biggest number that we have left. Minus, how many groups of 67 can I take out of 143?
2.
2 times 67. Okay, so 2 times 67 is what, 9? And now we get 67 minus how many groups of 9 can I take out?
7.
7. And that leaves me with what? 4?
4.
And then 9 minus 2 groups of 4 is equal to 1. And hey, now we're cooking with stuff. We like ones. All right, so now becomes the intricate puzzle of working backwards. So we don't like 4. 4 is no good for us. Instead of 4, we're going to put 67 minus 7 times 9. So 1 is equal to 9 minus 2 times 67 minus 7 times 9. And so this will give me what? I would have negative 2 times 67, and then plus 15 times 9 equals 1. Are we okay with that?
So why do we have to get rid of the 4?
4 does not help us in terms of solving. So like 4, we want it only in terms of 210 and 143. And so to do that, we have to slowly work our way backwards till we get to only 210s and 143s.
Okay.
Yep. Where's the 9? The 9 was just from right here. So this was 1 times 9, and this was 14 times 9. So I added them up and got 15 times 9. Okay, now we got 9s. 9s are really 143 minus 2 times 67. So minus 2 times 67 plus 15 times 143 minus 2 times 67 equals 1. Yikes. I'm running out of room, gang. I'm gonna have to erase this above line. And so if that's true, we can say that this is 15 times 143. And this would be minus 30 times 67. So this is -2 times 67, so minus 32 times 67 equals 1. And sometimes if you're a little worried about it and you are allowed to have a calculator, then throw this in your calculator and make sure you're still on the right track. This still checks out for us, so we're okay. And then to the final step, 67 is 210 minus 143. So this is 15 times 143 minus 32 times 210 minus 143 is equal to 1. So this will give us negative 32 times 210 plus 32 times 143, which then brings us to 47 times 143 equals 1. And now I rewrite this because I don't really like the way it's written here. This is 210 times negative 32 plus 143 times 47 equals 1. And so our solution, or one of our solutions, is 32, 47. Where'd you get 47? I got 47 from 32 times 143 and 15 times 143. That gave me 47. Yeah. Take a second and ruminate on this. Really let it sink in. Give yourself a second. All right, so let's walk through this process one more time. We dealt with 210 and 143, realizing they're relatively prime. We used the Euclidean algorithm to realize that this was really the same thing as 143 and 67. These two numbers are also relatively prime. And so we kept breaking that down. So we got 143 minus 2 times 67 is 9. And then again, now we'd be down to 67 and 9. And so we said, oh, well, 67 is really 7 times 9. And so that gave us 4 and 9. And then from there, we get, 4 and 1. And so from there, we end up with 1. 1 tells us that it's relatively prime. So this is why this had a 47. And here's why we had, or 67. This is why the 67 and 9 are there. And then here's where the 9 and 4 came in. And once we hit 1, we know we're gold. If we hit 0 or something like that, that means that these weren't relatively prime to begin with. All right, why don't you try one? Try it out. That one's big. I'm aware of that. But give yourself a couple minutes, try it out. All right, so if we have this, we do 255 minus 9 times 28 is 3. Then we realize that this is really 28 minus 9 times 3 is 1, which is great because then we already have 1, right? So we say, okay, well, what is 3? 3 is really this. So it's 28 minus 9 times 255 minus 9 times 28 is equal to 1. And so then I multiply out, I get negative 9 negative 9 times 255 plus 81 times 28 equals 1. And then I still have this extra 28 right here. And so that just gives me 82 times 28. And this would be 255 times negative 9. So our answer is negative 9 comma 82. What do we think? How do we feel about it? Do you guys want one more?
Can you go over the distributing part again?
Yep. So once I get 1, right, then we essentially break it down to what we had, right? So we say, okay, well, the only things I really care about are 255, 28, and 3. So I got 28 and 3. And so now I had to break down 3 in terms of 28 and 255. So I replaced the 3 with 255 minus 9 times 28. And then I distribute that -9 out front. So this became -9 times 255. And then -9 times -9 gave me 81 times 28. And so I had 81 times 28 and 1 times 28. So that gave me 82 times 28. And then plus 255 times -9. So what do we think? We want another one, or are we okay to move on?
But Mister, why didn't you distribute the -9 28?
So we're distributing it to the whole number itself, right? Kind of like if we do 2 times 10, that's just 20. We don't go 2 times 5 and go, well, that's technically 2 times 2 and then, or essentially like 4 and 10. Oops, let's see if I can go back to this. 4 and 10, right? We just say, hey, this is the same thing as 4 times 5. As long as I'm distributing it to one of the numbers, I don't distribute it to both.
Thank you.
Yep, because again, remember, these are products, so we just multiply them once. When we multiply it twice, it's because inside here, this is a subtraction. It's kind of like a binomial between the two. We want one more? I give you one more. 55x plus 63y equals 1. That should be a smaller one for us. Who knows, though? Could get wild. Okay, so I get here, right? I broke it down and said 63 minus 55 is 8. 55 minus 6 times 8 is 7. 8 minus 7 is 1. Okay, so someone work me through, how can I get to our final answer? What do I have to do?
You substitute the second to last equation into the last equation.
Yeah, so this becomes 8 minus 55 minus 6 times 8 equals 1. And so I distribute the negative. So this is a -1 times 55. And this is a plus 6 times 8 plus 8 equals 1. So that's -1 times 55 plus 7 times 8 is equal to 1. Okay, now what? Someone else help me out.
You substitute the 8, like 63 minus 55 for 8.
Yeah, now we substitute the 8 in. So this is -1 times 55 plus 7 times 63 minus 55 equals 1. And so that's 7 times 63. And this becomes -7 times 55 equals 1. And this is a -1 times 55. So that gives me 7 times 63 minus 8 times 55 equals 1. So 7 comma -8. No, wait, sorry, just kidding. Did it the wrong order. It should be -8 comma 7. There we go. Okay. Questions, comments, concerns? All right, guys, that's all I got.